This is 2011 AP Calculus AB and BC, so this actually appeared on both AP exams in 2011. But this is free response question number 4, and we weren't allowed to use a calculator on this question, so all the work you're going to see done here had to be able to be done entirely without a calculator. And it's a weird sort of problem because they give you this graph and they tell you that your graph is going to be 2 quarter circles. So you have a quarter circle with a radius of 1 here, you have another quarter circle here with a radius of 3 units, and then you have this line segment. They define this function g of x to be equal to this. So it's based on the graph of f, which is already provided, and f is within this integral, you'll notice. And then g also has this other tiny little piece, this 2x to it as well. In part A, we're asked to compute g of negative 3, define g prime of x, and evaluate g prime of negative 3. So to find g of negative 3, you're just going to toss negative 3 in place of the x's in the function g of x, just like you'd normally do any function evaluation. Now the one thing that you should hopefully notice is that these limits of integration aren't in the right order for us to use the area arguments that we like to use whenever we're dealing with definite integrals. So you can flip the limits of integration, like I did here, as long as you change the sign out in front of the integral. And then 2 times negative 3 is obviously negative 6, and then it was just a matter of trying to evaluate this. Well, this is going to correspond to the signed area between f and the x-axis from negative 3 to 0. So from negative 3 to 0, all we're dealing with is this quarter circle. So if you find the area of that quarter circle, that'll give you your value of g of negative 3 once you subtract it from the negative 6 that we already had established. To find the derivative of g of x, well, the derivative of 2x is pretty simple. That's just going to be 2. And then the derivative of this is going to require the second part of the fundamental theorem of calculus, which is stated right here. So you're taking the derivative with respect to x of a function whose x is actually the upper limit of integration. That's going to allow you just to replace the t, or the letter that you see within the integrand, with x, and that's going to be your result. So g prime of x is actually going to be equal to 2 plus f of x. G prime, we're just going to toss negative 3 in place of the x in g prime, and f of negative 3 right off of the graph is 0, so g of negative 3 is going to have a value of 2. If we move on to part B, I kind of took the long approach in part B, so we'll kind of talk about what I did very briefly, and then after I finished this I realized there was a little bit better way to go about this. But what I realized was if I'm looking for an absolute maximum of a function, I need to have my candidates in line. It could be endpoints of a closed interval. So I have an endpoint of negative 4 and another endpoint of 3. And they could also be critical numbers, places where your derivative is equal to 0 or places where your derivative is undefined. Our derivative, g prime of x, is always going to be defined. F of x is always defined from negative 4 to 3, so we don't have to worry about anywhere where our derivative is undefined. But to find where g prime of x equals 0, if you put 0 in for g prime of x like I've done here, and then solve that for f of x, it basically says f of x has to equal negative 2. So anywhere on the graph of f where it equals a y value of negative 2, that's going to be an x value that makes g prime equal 0. So I did notice that if I look at the y value of negative 2, there's only one point where that happens. That happens at the x value of, well, I'm not quite sure what it is. I kind of tried to draw it very roughly here, but I realized it was on this line segment. And so if I found the equation of this line segment, I could set the y value of the equation of that line equal to negative 2 and then solve for x. That's what I have done right here. So you know I had this point 0, 3, rise of negative 1, 2, 3, 4, 5, negative 6, a run of positive 3 taking me to this point. So my slope was negative 2, negative 6 over 3 reduced to negative 2. And then the y-intercept of that line is nice because it's given, it's 3. So the equation of that line would be here in slope-intercept form. I want to know when on that line y is equal to negative 2. So I solved that for x and got an x value of 5/2. What I attempted to do on the next screen is I attempted to evaluate the function at these candidates. So I evaluated it at g of negative 4. That took a little bit of work. It was similar to evaluating g of negative 3 like we had done in part A. I had to use a little flip of the limits of integration, some area arguments down through here, and I got this value for g of negative 4. And then for g of 5/2, I just tossed 5/2 in place of the x in the x's in the function g of x, and I ended up using area arguments to find this. So I had an area of a triangle right here that was above the x-axis, so 1/2, base was 3/2, height was 3, and then I had an area below the x-axis right here that was also a triangle, and that was going to be given by 1/2, base of 1, and then a height of 5/2. So I ended up with a value of 6 after it was simplified for the value of g of 5/2. I didn't bother finding g of 3 because our function is going to be decreasing on the interval from 5/2 to 3. So I didn't bother finding it, I just kind of eliminated it that way. So the absolute max is at g of 5/2, and it's a value of 6. What I could have done here is I could have, if we go back a screen, I could have realized, well, this derivative, g prime of x, is going to be positive as long as f of x is greater than -2. So g prime is positive here, since f of x is always above -2, and then it's negative from this value, x value, to this x value. So it's negative on this last little interval. The function g is therefore increasing, since its derivative is positive on this entire interval. So it increases until we get to 5/2, and then it decreases here. And that's another way that we could have more easily determined that we had the absolute max at 5/2. The derivative is always positive until 5/2, and then always negative after 5/2 until we get to 3. So either way you do it, we have an absolute max at the x value of 5/2. In part C, we were asked about points of inflection for the graph of g. Well, to answer questions about inflection points, you need to know where your concavity changes. We have a point of inflection anytime you change from concave up to concave down, or vice versa, on your function. So I wanted to find the second derivative, because when the second derivative is positive, our function's concave up, and when the second derivative is negative, our function's concave down. So I had my derivative that we'd computed earlier, g prime of x here, and then when I take the second derivative of that, the derivative of 2 is 0, and then the derivative of f of x is f prime of x, so g prime of x is actually equal to f prime of x. Well, f prime of x is going to correspond to the slope of the tangent line anywhere on this graph. And we have positive slopes everywhere we look here. We have an undefined slope here, and then we have negative slopes until we get to this endpoint on the graph of f. So since the slope of the tangent line to this graph is going to represent f prime of x, which also represents g double prime of x in this case, the only time that g double prime changes signs is when f prime changes signs as we cross the x value of 0. We go from positive slopes here to negative slopes there. So our only point of inflection is going to be at x equals 0. And then in the last part of this, it wants us to find the average rate of change of the function f. So we're no longer dealing with the function g in part D, but the average rate of change of the function f on the interval from -4 to 3. So an average rate of change is just going to be the slope of the secant line connecting the endpoints of this interval. So to connect these endpoints with a line segment and then find the slope of that line segment, it's not that big of a deal. It's just the regular old slope formula. So I took this y value minus this y value over this x value minus this x value, and I got a slope of -7/2. So the slope of this line segment, if I was drawing it in right here, would be -7/2. Now, there is not a point in between -4. The slope of the tangent line is not going to equal -7/2 anywhere between these two x values. The reason why this doesn't violate the mean value theorem is because, well, the mean value theorem requires you to not only be continuous, which this graph is, but also to be differentiable. And because we have this cusp right here, where the slope of the tangent line changes from 0 right at the top of the circle to a -2, we skip the slope of -7/2 because we didn't have a gradual change with the slope of our tangent line. We had this rapid change. So the mean value theorem doesn't hold here since our function is not differentiable on this interval.